Thank you for coming to my presentation. I'm Seokjoon You. I'm a research engineer of HANMEC Engineering since 2017, working in the field of software development. I guess many of you are less familiar with my company, so let me introduce it shortly. HANMEC Engineering is an infrastructure design and engineering firm founded in 1996. It has designed many highways, bridges, and tunnels in South Korea. It is rather a small company in terms of its revenue, which is roughly $36 million in 2020. Actually, it has 4 sister companies, some of which earn more money. Its sister companies include another design and engineering firm, 2 precast concrete fabricators, and 1 environmental engineering company. The main topic of my presentation is about digital transformation of the infrastructure design and engineering, especially using digital twins. This presentation has 5 sections. The first section shows the problems that need to be solved with digital transformation. The second section discusses on our vision of the digital transformation is the future of the infrastructure engineering we see. The third section describes the components that forms the digital transformation. The last section discusses the things that need to be done to realize the transformation, plus a brief description of what my company is doing for our digital vision will be given. Section 1 on problems. One of the reasons why we are focusing on the digital technology is because the traditional engineering techniques are not sufficient to keep the civil and infrastructure engineering competitive. As you look at the left side graph, it shows the productivity trends of construction compared to manufacturing and other economic areas. According to this graph, construction ranks the lowest, and its annual trend is not really impressive. Low productivity is in the financial trouble for the contractors, and it also causes great concerns in terms of public safety. From the experience of other industries, low productivity seems to be caused by low level of automation. Qualified technicians are scarce today, so if automation is not sufficiently employed, the quality and the safety of the infrastructure will be in danger. I also want to mention some South Korean specific issues, though I suspect that other Asian countries have similar issues too. Population aging, for instance, seriously affects South Korean economy. More money needs to be spent for taking care of the elderly people, which causes reduction of new infrastructure investment. Also, as many skilled laborers are aging now, they are retiring without a new supply of young workers, which is detrimental to the industry's future too. As a result from the tightened budget, there will fewer new infrastructure projects, and the business competitions to get the project will be tougher. To survive those tough competitions with extra public benefits regarding safety and more, smart construction came up. Section 2, vision. Our claim is that low productivity can be improved by automation, and information technology plays a key role in automation. We call it smart construction because the automation powered by the information technology makes the traditional construction engineering smart. Of the smart construction, there are 2 aspects, hardware and software. When we build a physical structure like a bridge, we use various machines and tools, that's hardware. For smart construction, robots and equipment automation are the examples of the hardware aspects. On the other hand, when we design the bridges before we build it, we perform intellectual tasks such as analysis and calculation, often with soft computer software. So engineering firms such as my company, software aspect is the main focus area of smart construction. As all of us have experienced, many parts of our everyday life have been digitalized. I think that such digitalization has been done incrementally for decades. When I was a kid, video games took over kids' playground somehow. When I went to college, personal computers running word processors replaced notebooks and pencils. Not long after that, every engineer was using CAD for drafting instead of T-squares and triangles. Such transitions still continues today. Digital transformation is pushing such change forward, the point where synergy is achieved by advanced software systems and by integrating them, combined with networking, advanced digitalization that allows further innovations, not only for the technologies, but for the business processes and the way we understand them. Let's talk a bit more about digital transformation. Digital transformation implies a fundamental change of existing business practices. For civil and infrastructure engineering field, we see the transformation will be implemented by digital twins. Digital twin is a precisely duplicate virtual world where civil infrastructure can be built, measured, and demolished. Events that happen in the real world infrastructure can be duplicated in its virtual twins too. Simulation in the virtual world against the digital twin is the key for making such a synchronization possible. From the perspective of digital transformation, digital twin has several advantages. The stakeholders of the infrastructure can communicate over the virtual world with it. The virtual world can overcome the spatial and temporal limitations of the real-world communications. Therefore, digital twin allows us to innovate how we work. Section 3, components of digital transformation. Now let's dig in a little bit about how to implement such a digital transformation. Just as I said, digital twin is a key to the transformation of the construction industry because digital twin technology can address various lifecycle management issues of infrastructure. When we implement the digital transformation based on the digital twin, it will consist of 3 key components: data model, software, and service platform. First, a data model. A data model represents a real-world existence or a concept into a structured data format. Virtually, all computer systems that handle the real-world phenomena, from bank ATM to power plant controllers, use such models. Therefore, the data model can be seen as a gene of digital transformation. For digital twins, the data models are rather individual elements showing their shape. For computer software, data model is crucial to its functionality. There are many different kinds of engineering software for design analysis, cost estimation, and more. The software can recognize the digital design because data model provides the vital information of interpreting the data. As digital transformation applies to the entire life cycle of the infrastructures, its data models will evolve as it goes through the life cycle stages. However, even each stage requires different data, they share common data elements, which needs to be clearly defined in the data model. Second, software. The second component is software, a source of digital transformation. The data model defines what the infrastructure is. Such a definition is done by an engineer using software. To achieve the higher automation level, there must be a new breed of software that caters for the new digital twin-based business process. The new software must satisfy the following features. First, it must help the user handling higher precision and larger volume of information provided by the digital twin models. Typical human engineers will have difficulties in handling them manually. Second, it must provide a certain level of automation for the task it is used for. Although full automation of engineering design seems a dream for now, but automating basic tasks such as document generation will still be helpful. Third, it must embody the business knowledge and processes that are needed for the engineering. Such knowledge needs to be captured to the software. This requires close collaboration between the engineers and the software developers. The last component of our digital transformation triad is a service platform. The platform is a special kind of software which provides online service to its users over a network. is called a platform because the service may target other client software and serves as a common component for the software. For our digital twins, the platform hosts the data model and manages the data collection based on it. The collection includes the core data components of the digital twin, which is shared by multiple stakeholders throughout its life cycle. Also, a data collection which is specific to an individual stakeholder or certain life cycle stage is called a model view, which is also served by the platform. For digital twin-based life cycle management, its service platform must provide two key functionalities. The first functionality is to manage simultaneous access to the platform. Also, it should manage the interactions between the users. The second functionality is to manage the change of the data collection. As multiple changes occur simultaneously, they have to be coordinated to avoid any conflict. Also, history of the change should be kept so that they can be tracked down later or cancel them if needed. Section 4, changes. To this point, we have covered what the digital transformation is and its main ingredients, which is implemented as digital twins. Now, I'd like to discuss the changes as a result of the digital transformation. The biggest change we see is that the virtual side of infrastructures will be more visible to the stakeholders and more business will take place in the virtual side of they are now. For instance, the digital twin of existing condition, as you see in the upper left side of this slide, allows pre-construction planning in the virtual world with the benefits of advanced visualization and better software support. In this virtual world, the digital twin model's behavior will precisely simulate its physical twins, including its interaction with people and equipment. Software made for the digital twins will provide the real-world like user experience for its synthetic work, combined with the visualized parameters and the analysis results. For the contractors, the construction process will become more like reconstructing the virtual model components in the physical world. New automation technologies such as computerized prefabrication, large-scale 3D printing with advanced material will enable automated reconstruction of the virtual model. If the design and engineering phase, the design alternative can be virtually built and simulated until an optimal alternative is found, which means virtually the designer will have to do many of what contractors do now for the physical construction. The biggest change will happen to the scope of the designer role in the life cycle of the infrastructure. This virtual world allows broad involvement of the designer because she has actually constructed a virtual model. If the model is synchronized with its physical twin, many of the maintenance work such as monitoring will be possible within the digital twin. Such change also implies some challenges. One of them is that both quality and quantity of the information produced by the designer will increase and well beyond what current business practice expect. The designer must be capable of dealing with the information at the early stage of the project. Possible solution for this change is automating the design and engineering process, which is done by the intelligent software. Making the intelligent software means that such a software is a professional knowledge needed for generating design and engineering information, which is realized by capturing the know-how of the individual and an organization of the design and engineering business. Therefore, for the design and engineering firms, the capability of capturing the professional knowledge and possibly packaging the captured knowledge into the intelligent software will become more important. Section 5, things to do. Now, the final section of my presentation. Here I will cover key technological developments, organizational and industrial readiness that to be achieved. Key technologies for the digital transformation, including digital twin, have been available for years or decades. However, some of them need to be more mature. For instance, 3D scan technology still has room to improvement, such as accuracy, scanning speed, blind spots, etc. For modeling the virtual world and the infrastructure, large-scale modeling is still an issue, but the technologies for handling the geometry are advancing now. more important thing than the geometry is to create an information model which can hold vast areas of information from all the aspects of the infrastructure life cycle. Making such a model is difficult because many of existing business practices haven't been digitalized, and some of them are hard to translate visually. For example, budgeting and scheduling tasks. Maybe the tougher part is capturing the design and engineering knowledge and packaging them into the intelligent engineering software. Recent advancements in artificial intelligence, such as deep learning, may give some clue regarding for this. But traditional knowledge bases or even programming languages may also provide a solution if the communication between the engineer and the software developer is frequent and well organized. For hardware-wise, such as robots and machines, many issues have to be solved to make a breakthrough. However, I'm not covering the hardware stuff here, which is well beyond the scope of this presentation. As we already have experience in personal and mobile computing areas, when some technological advancements have been made, cultural and sociological change also follow. With the digital transformation for the civil and infrastructure engineering businesses, organizational and cultural change will affect the entire life cycle of the infrastructure afterwards. What we see is the change will be more fundamental to the existing business practices. The expansion of the designer's role and the better accessibility to the digital twin platform for the stakeholders, the boundaries between the stakeholders, as well as the ones between the business areas will be blurred. Also, technology will change the business processes of industry. Such changes have always occurred as new technologies become available. However, preparing for such changes in advance will be helpful if it gives competitive advantages. So the bottom line here says respond proactively rather than reactively. Now the last slide. In this slide, I'd like to cover briefly what we are doing at Hanmek Engineers Tech Development Center. The center was started in the early 2010s as a small group of engineers and software developers to implement intelligent engineering. These early efforts are targeting to our internal needs, such as drawing management and document generation. However, we are now moving toward their twin-based digital transformation. Here are some highlights of our development efforts. First, the models of topographic information and GIS, in-house model processing and viewing modules are being developed. The geographic modules can interpret with our engineering modeling software, so the virtual structure can be shown on top of the virtual terrain information. The model of the roads and the structures are generated based on the logic developed under close collaboration between our civil engineers and software developers, allowing the engineers' expert knowledge to be captured into our software. For simulation, the simulation capability of the digital twins, structure analysis module, and construction simulation modules are under development. Realistic visualization capture capabilities supporting virtual reality and extended reality have been implemented to support the digital twins. Also, a part of government-funded smart construction research platform technologies for sharing the digital twin models are under development, which includes their standards and a common data environment for the precast concrete product delivery. Okay, that's all. This concludes my presentation, and I appreciate all for joining me. Thank you.